Alright, hey guys, what's going on? So today we are going to be talking about the exterior algebra. We're inching towards the exterior product. Or not the exterior, yeah, we're inching towards the exterior product. This is going to be, and the exterior product is going to sort of shoot us from the topic of tensor calculus into the topic of topology a little bit. But I'm still sort of staying within the purview of tensor calculus because that's what this playlist is all about. And right now, again, we're talking about p-forms, we're talking about anti-symmetry. What kind of restrictions does anti-symmetry place on us? And where this sort of takes us down the rabbit hole of talking about forms, exterior products, topology, homology, cohomology, and all that kind of stuff. And so with that being said, make sure to hit that like and subscribe button. Make sure to go to my Patreon page if you want to support the channel. Again, things are going to be changing up there just because I don't really like how I've sort of been trying to balance between this and my Patreon page. And again, yeah, so things are going to change there. But with that being said, again, make sure to hit that like and subscribe button. Now let's get into the topic. So today we are talking about the exterior algebra. So right off the bat, I actually want to show this to you right off the bat. This I think is going to be very useful. So I took the liberty in, again, we're dealing with an underlying four-dimensional space right now, because when we're talking about GR and when we're talking about special relativity, our underlying vector space is 4, okay? We have dt, dx, dy, and dz, okay? So that means we have a 0 form, a 1 form, a 2 form, 3 form, and a 4 form, okay? And this is all to say that functions are the 0 forms. We have small distances being the 1 forms. We have areas being the 2 forms. Then I have these quotes, right? Distances and functions, right? So these are, we can sort of maybe think of them as pseudo distances right now or pseudo functions, but again, the reason I'm calling them that is because in the last video we were able to show that the Hodge dual of these guys. These guys were Hodge duals of each other. These guys were Hodge duals of each other. And this guy is a Hodge dual of itself. All right. So this is sort of the punchline we're going to get to with this video, because here you could see that I have this D now. Okay. This D is the exterior derivative. Okay. And we're inching towards that. We're sort of slowly getting to the idea of an exterior derivative, which we're going to flesh out more in the next video. But right now, let's suppose we have a P form and a Q form, okay? We can write our P form in this way. We can write our Q form in this way, okay? And again, alpha has to be less than beta. We're going to see how this can also be written later. But when we wedge these two guys together, what we do is we say, well, here's our D gamma. When we wedge it together, we have to, and we want to bring it to the front, well, we're going to have to wedge it. When we inch it towards the front, like we've sort of shown in the last video, we have to introduce a negative sign every time we do that. So we're going to have to do it P times because it's going to have to go in front of P objects. Okay, so that's going to be minus 1 to the P with this guy. Then we're going to have to do the same thing for delta here, right? So we're going to have to do the same thing for delta here, and then whatever is after that, Q times, right? Because we have Q things over here, and we have P things in here. So the fact that we have to do that Q times means that this is when we wedge omega with eta, we get minus 1 to the PQ. That's where that Q comes from, because we have to do that Q times. So therefore we have this identity that whenever we wedge two things together, whatever the whatever forms they are, That's going to tell us what factor of a negative sign we put out in front. So therefore, so far what we've seen when we've talked about forms and all this kind of stuff is that we have the wedge, which takes us to the P plus Q form. If we're wedging a P form with a Q form, we get P plus Q form, and now we have this rule. Okay. Let's talk about the inner product. So when we talk about vectors, if you recall, when we talk about vectors, let's write here's our manifold. Here's our manifold, and here is our underlying vector space. Initially, we introduced this idea of a wedge, or not a wedge, we introduced this idea of an inner product in that vector space. And when we introduce that inner product, we get an inner product space. Okay. So, and now we've talked about this idea of a wedge or an exterior product space. So the question is now, is there such thing as an inner product in that space? And the answer is yes. Right. So let's sort of give an intuitive understanding of what this could possibly mean, or what an inner product could possibly mean physically for us. So let's do an example. Given that we have, let's say that we're given these two guys, dx dy and dy dz. Let's say if we're going to suppose right now that the inner product is the determinant of all the combinations of these two guys that we can get. Okay, so dx dy, here's our dx dy, dx dz, here's our I should have a dx dz in here. So here's our dy dy, so dy dy, and then dy dz, dy dz. This guy should be an x, right? That should be an x. So everything still works out here, because if we notice, when we take that determinant, this is still going to be 0. So nothing changes on behalf of my calculations here. But when I made that x change, because this is 0, the inner product between dx and dy is 0, because they're orthogonal to each other. Inner product of dy dz is 0, inner product of dx dz, because those are all orthogonal to each other. The only one here is going to be 1, right? So the determinant is 0 minus 0, right? Because we have this 0 in the off diagonal. So that's just going to be 0. And we can, again, think of these guys as areas. So when we wedge dx dy, that's this guy right here. And when we wedge dy dz, that's this guy right here. Okay. How about dx dy? All right, so dx dy, dx wedge dy, dx wedge dy. So we're taking the inner product of something with itself. It should be 1, right? Whenever we take the inner product of something with itself, it should be 1. So when we do that, we actually do see that, because this is going to be dx dx, that's going to be 1. This guy is going to be dx dy, right? The dx dy, so this guy's going to be 0. Then we have dy dx, right? dy dx, and then dy dy down here. So we're going to get 1 minus 0, that's going to be 1. All right. That, and these two guys are this area right here. Okay, so we have, what we're actually doing here is something quite interesting. We are generalizing the idea of an inner product for wedge items, right? So for areas. Let's take a look now at dy wedge dx, right? So dy wedge dx, that's going to be this area right here, and then dx wedge dy, right? Well, dx wedge dy, well, that's minus 1 times dy wedge dx, right? Because we bring that over, and whenever we bring that over, we bring that to by a factor of 1 because of the anti-symmetry. So this area dy wedge dx is one of these areas. The other one is going to be this one. It depends on, again, how you define negative directions in our frame here. Let's actually, I want to do something different here. I want to say that this one is the green. So actually, I'll just label it green. This is the green area. This is the red area. And right, because this here, the reason I'm doing that again is because dx is the same thing as dx1 wedge dx2, right? So that these two guys are the same, and these are in higher order, or these are in 1, 2, 3. That's the order that we typically want when we're looking at forms. And so I'm defining this plane to be the positive plane, and then this plane to be the negative plane. Okay, well, so that's all sort of plus minus semantics, if you will. However, when we do the inner product here, we can sort of, get this in the screen. dy dx, that's going to be this guy. And then dy dy, that's going to be this guy. That's going to be 1. So this guy's going to be 1. dx dx, this guy's going to be 1. And then dx dy, this guy's going to be 0. So the diagonals are 0, but the off diagonals are 1. And so we get 0 minus 1. And so we get negative 1. Okay? So this is the idea here. The idea is whenever the areas are the same, we get 1. Whenever they're at a 90-degree angle to each other, we get 0. And then whenever they're at a 180-degree angle to each other, we get negative 1. So the inner product's now been generalized to areas. Where so in the case where inner product was between vectors, right? We could either get plus or minus values. Okay, if the inner product was 0, then that would mean that there's no agreement between the two vectors, right? There's no, here's one vector, here's another vector. In this case, again, the inner product tells us something about how much the two vectors agree with each other, right? So it'd be this, that tells us, the inner product tells us that distance. However, if our vectors are like this, suppose that's one vector, that's the other vector, that's a case where the inner product is 0. Okay, so we've generalized this to areas. So for the P exterior product space, the inner product is going to be given by this formula right here. Okay, so now we have this idea of what an inner product looks like for our spaces. And so now we have this picture on our manifold where we have P, dimensionality, and an inner product in this space as well. The next question would be, is there a way we can relate these two to each other? That we're not going to do in this video, but it could be something interesting for later. We also want to take note, so I sort of glossed over this before, but we also want to take note that if omega is within P, well, then we have to write it. If we write it in this way, right, if we just write omega, in its component form, there's actually this 1 over P factorial involved, right? So if we go back to here, we actually need a 1 over p factorial, and we actually need a 1 over q factorial in here. Okay, and then those are going to both get carried down. If I move this guy a little bit, those are both going to get carried down 1 over p factorial, q factorial. Okay. So that's something we also know. And that just accounts for any replication process here, right? Because here I'll show us why. A 2 form, for example, say dx0, dx1. Nope, I'm gonna do it like this, right? So we said that the wedge product was like this. Oh, no. So this is our wedge product. We've sort of established that already. That's the wedge product. So if we write omega equals omega 1, 0, 1, well, this already has the omega 1, 0 in there, because that omega 1, 0 is right here. So omega 0, 1 already encapsulates omega 1, 0, so we need to account for that, and the way we account for that is by dividing by 2, okay? Which is also the same thing as 2 factorial. And when you do all of that for, say, 3 forms, 4 forms, 5 forms, it just becomes 2 factorial, 3 factorial, 4 factorial. We're just accounting for that replication. Okay. So another way of writing that is with these lines, which is what I've done before. The lines mean that mu always has to be less than nu, because if it's not, then again we wouldn't be accounting for that the anti-symmetry that I literally just talked about. So if omega p, or so if omega is part of a p form and eta is part of an n minus p form, then omega wedge eta is going to be p plus n minus p, which is just part of an n form. That is the top form, right? So I'm actually going to put that, this is going to be the top. This is some vocabulary. That's just nice to know. Because we're also going to talk about closed forms and exact forms. And top forms, closed forms, and exact forms are things that we need to know for topology reasons. So we have closed forms and exact forms. And we'll talk about these guys later. Okay? But all of these guys are necessary ideas for topology, homology, cohomology. So all of these different areas of mathematics all require this understanding of a top form, closed form, and exact form. Okay. So in sum, if we wedge omega with eta, we get it 1 over n factorial. That's the top. That's what it means to be inside the top form, because we need to account for all of that replication again. These are all just numbers. These are all just coefficients on our basis vector, which goes from I1 all the way to j to n minus p, j of n minus p, right? Because the coefficients again on eta go from, here I'll expand this a little bit, they go from dx j one wedge. These are part of eta. And then these guys will wedge to dx I p. These are part of omega. So that looks a little bit messy, but again, I kind of just expanded that. Okay. All right. So why are p-forms so interesting? First, we need to take the derivative of them to find out the answer to that question. That's going to be the topic of our next video. And the derivative of p-forms is something called an exterior derivative. So the exterior derivative, we're going to get into this a little bit deeper, but say omega is a p-form. Either the exterior derivative of an omega is going to be given by something like this, right? So if omega is a p-form, then it goes from omega I of 1 to I of p, again, where these are just numbers. And that can be encapsulated into something that looks like this. This is something you'll see quite a bit. This is just notational stuff. But the idea, again, is we want to take the derivative of omega. Right? We want to take the derivative of omega. When we do that, we have to take the derivative with respect to its coordinate. And that's going to hack on this dxj to our already pre-existing dxi. Okay, so what does that mean? That means that our exterior derivative is going to take us from a p form to a p plus 1 form, right? Because of this guy right here. So the derivative of a p form is a p plus 1 form. So suppose our underlying vector space, again, is 4 dimensions. This is this is our top form right here. We have all these dimensions for our spaces. If omega is a top form, then d omega equals 0, right? Because you can't get anything higher than a top form. So if omega is part of, say, this in this space, right? The derivative is going to be in this space, okay? Because it's p plus 1. All right. So the two properties of the exterior derivative are going to be these two guys right here. And we're going to actually derive these in the next video, right? So the derivative of the derivative of a form is going to be 0, and the derivative of two forms together is going to be this right here. Okay. And so we come back to this picture that I showed us before, where we have, again, the brown lines are the Hodge dual mappings. The D's are the exterior derivatives, and this is all within an underlying vector space of 4, or an underlying vector space dimension of 4. Okay, and so this is what we got, right? So you can imagine if we had an underlying vector dimension space of 7, 8, 9, or 10. This gets so much more complex because we have so many more spaces that we have to take into account. But anyways, that is a rundown of what we talked about here was really just talking about notational things. We talked about the inner product of within these spaces, right? So that's actually something worth noting. We have inner product spaces everywhere here. I'll just draw them out in this color. We have an inner product here. We have inner product here. We can have an inner product here as well. And we have an inner product in all of these spaces. All right. So that's our complete view of forms on this manifold. Again, the manifold is M. And with that being said, I don't want this video to go on for too long. Make sure to hit that like and subscribe button. Make sure to go into my Patreon page and if you want to support the channel. Again, things are going to be changing up there. I know I've also started a biophysics playlist. I don't really like how the direction of that biophysics playlist is going, so I think I'm going to be changing things up on that end as well. But with that being said, again, make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.